Our future home could be a city floating in the clouds of Venus. This is the breathtaking vision of terraforming our sister planet, a plan that could redefine humanity's place in the cosmos. By the end of this journey, you will understand the science and staggering ambition behind turning a scorching hellscape into a second home. We will explore how floating metropolises might drift above the acid rain and what planetary-scale machines could rebuild an entire atmosphere. What does it truly mean to reshape a world, and are we ready for that responsibility? Venus is a world of extremes that defies our earthly intuition. Its surface is not simply hot. It is a furnace that could reduce metals to liquid, with temperatures soaring to 465 degrees Celsius. The pressure there is immense, equivalent to the crushing weight found nearly 1 kilometer beneath Earth's ocean waves, but here it is applied by a dense, toxic atmosphere. This is not a place for machinery, let alone life as we understand it. The very clouds that shroud the planet are not made of water vapor, but of corrosive sulfuric acid, completing a portrait of a profoundly hostile environment. This terrifying reality is the direct result of a runaway greenhouse effect, a process that spun wildly out of control billions of years ago. Sunlight penetrates the thick atmosphere, but the heat it generates becomes trapped by a blanket of carbon dioxide, creating an oven that has been baking the surface for eons. Our robotic emissaries have borne witness to this hellscape. The Soviet Venera landers of the 1970s and 80s transmitted the first and only images from the surface, showing a desolate, rocky plain before succumbing to the overwhelming heat and pressure within mere hours. Later, NASA Magellan probe used radar to map the entire planet, revealing a landscape of volcanoes, vast plains of solidified lava, and tectonic scars, all hidden beneath that perpetual, acidic cloud cover. These missions delivered a clear, data-driven verdict, establishing a permanent foothold on the Venusian surface with current technology is not just difficult, it is effectively impossible. The environment is too punishing, too relentless. This fundamental truth forces any realistic vision for a human future on Venus to take one of two radical paths. We must either build our homes safely above the fury, in the more temperate skies, or we must embark on the monumental task of changing the planet itself. This is the fork in the cosmic road where our story truly begins. This impossible surface forces a radical shift in perspective, literally looking upward for a solution. The answer lies not on the ground but in the sky itself, within a narrow band of the Venusian atmosphere. At an altitude of approximately 50 to 60 kilometers, something extraordinary happens. The crushing pressure eases to a comfortable level similar to what we experience at sea level on Earth, and the temperature ranges between 0 and 50 degrees Celsius, a far more manageable environment. Here, in this unlikely sweet spot, the dream of a floating city becomes a tangible engineering proposition. The core principle is beautifully simple. On Earth, we use helium or hydrogen in balloons because they are lighter than our nitrogen and oxygen air. On Venus, the situation is reversed. The planet's thick atmosphere is almost entirely carbon dioxide, a gas that is significantly heavier than the breathable air we would need to fill our habitats. This means a large envelope filled with a nitrogen-oxygen mixture would naturally float in the carbon dioxide sea, like a bubble of air rising in water. Our very breath becomes the lifting gas. Envisioning these structures pushes material science to its absolute limits. They would be vast, geodesic spheres or dirigible-shaped envelopes, engineered not from steel and glass, but from revolutionary composites and aerogels. These materials must possess incredible strength to contain the internal atmosphere while remaining ultralight, and they must be utterly resistant to the perpetual, corrosive drizzle of sulfuric acid that defines the cloud layer. Imagine a translucent city-sized balloon, its skin a marvel of nanotechnology, drifting serenely above an endless orange and white cloud deck. Inside, interconnected modules could house living quarters, agricultural biospheres, research facilities, and communal spaces, all bathed in sunlight filtered through the upper haze. This vision transforms the most hostile part of Venus, its atmosphere, into its greatest asset. The floating city is not merely a life raft, it is a foothold, a permanent human outpost established not by conquering the hell below, but by gracefully riding above it. It offers a stable platform from which the far more audacious second phase of this plan could one day be orchestrated, the long-term transformation of the planet itself. But could we ever truly tame such a world? Yet a floating metropolis, for all its elegance, is ultimately a sanctuary suspended in a hostile sky. It leaves the fundamental nature of Venus untouched, a beautiful prison floating above a world still locked in a deadly equilibrium. To truly claim this planet as a second home, we must confront the source of its fury directly. This leads us to the grandest and most daunting phase of all, atmospheric conversion, a complete planetary redesign. The core problem is starkly simple in statement, but staggering in scale. Venus is smothered under an atmosphere of carbon dioxide that is 90 times denser than our own. This is not a thin blanket but an oppressive, global ocean of gas, the very engine of its runaway greenhouse effect. To cool the surface, make liquid water possible, and open the door to an Earth-like environment, this immense volume of carbon dioxide must be removed, locked away, or fundamentally transformed. Think of it not as gardening, but as planetary-scale chemical reprocessing. One of the most discussed theoretical approaches involves forcing this atmospheric carbon dioxide to become solid rock. On Earth, this process happens naturally over geological time through silicate weathering, where carbon dioxide in the air reacts with certain rocks to form stable carbonate minerals like limestone. The vision for Venus would be to accelerate this natural thermostat by orders of magnitude, perhaps by bombarding the surface with pulverized silicate minerals from asteroids or the planet's own moons, creating a fresh, reactive layer across the globe. Another more speculative idea involves using colossal orbital sunshades to cool the planet dramatically, potentially freezing the carbon dioxide out of the atmosphere, where it could fall as snow or dry ice onto the now frigid surface. Each concept presents a maze of secondary challenges. Where would we get the unimaginable quantities of material needed for global mineral seeding? How would we construct and maintain sunshades larger than the planet itself? The energy requirements for any of these projects defy current human comprehension, demanding power sources we can barely envision, harnessed across centuries or even millennia. This is engineering not on the scale of a city or a nation, but of an entire world, a task that redefines the very meaning of ambition. It asks us to think in time frames that stretch beyond individual lifetimes, beyond civilizations, viewing a planet as a single, long-term project. The floating city provides the necessary foothold, the observation post and command center from which such a millennia-spanning operation could be slowly, patiently orchestrated. But before we can even contemplate moving mountains of gas, we must first address a more immediate and volatile obstacle, one that circles the planet in its upper atmosphere, a perpetual storm of acid and wind. The sulfuric acid clouds present a constant, corrosive rain that would dissolve conventional metals in a matter of weeks. This reality forces the first and most fundamental technological leap, the creation of advanced materials capable of not just surviving, but thriving in this alien sky. The entire concept of a floating city rests upon a foundation of substances that do not yet exist, pushing materials science into realms of radical innovation. Consider the habitat envelope itself, It cannot be a simple balloon. Its skin must be an intelligent composite, likely woven from carbon nanotubes or boron nitride fibers, forming a matrix that is incredibly strong yet feather-light. Embedded within this matrix would be layers of self-healing polymers, substances designed to automatically flow and seal any puncture from a micrometeorite or debris, maintaining the vital atmospheric seal without human intervention. Every external surface, from structural beams to sensor arrays, would need a permanent defense against corrosion. This could involve developing entirely new families of ceramic metal alloys or applying atomically precise coatings that actively repel sulfuric acid molecules, rendering the material chemically inert. Even the quest for power demands new inventions. Solar panels designed for Earth's clear skies would be woefully inefficient under Venus's perpetual, diffuse haze. Next-generation photovoltaics would need to capture a broader spectrum of scattered light, perhaps using novel perovskite cells or layered designs that mimic photosynthesis, turning the planet's gloomy glow into a reliable energy source. The philosophy of construction is equally revolutionary. Transporting millions of tons of material from Earth is impractical, so architects look to the environment itself. Could we mine the atmosphere, processing its abundant carbon dioxide and sulfuric acid to extract carbon, oxygen, and sulfur to synthesize building polymers and composites right there in the clouds? Imagine autonomous drone factories floating in the temperate zone, fed by atmospheric scoops, 3D printing structural components day and night. The logistics boggle the mind. Would we assemble entire city modules in orbit and gently guide them down into the atmosphere? Or would we grow them in place like crystalline structures forming in a solution? This intense focus on extreme material science carries a profound secondary gift. Every breakthrough forged for the clouds of Venus, every self-healing polymer, every ultra-efficient cloud solar cell, and every acid-proof alloy would inevitably cascade back to Earth. They could lead to longer-lasting infrastructure, new medical implants, or revolutionary energy systems. In seeking to build a home in the most hostile environment we know, we may well invent the tools to better care for our first home. Yet even the most perfect, resilient habitat is a silent tomb without a steady, breathable atmosphere inside. How do you create and maintain a bubble of Earth in a sky of poison? These resilient bubbles of Earth air would be meaningless without a way to fill and refresh them continuously. This leads us to the second technological pillar, the colossal machines that would literally breathe for a new world. To convert the atmosphere of Venus, we need to think in terms of planetary organs, vast autonomous systems functioning as artificial lungs and kidneys on a global scale. Envision atmospheric processors, each one a floating or anchored city in its own right, humming with silent, relentless purpose. They could be powered by immense solar arrays, soaking up the perpetual daylight above the clouds, or by next-generation nuclear fusion reactors, tapping into the fundamental energy of the stars. Their singular, monumental job is to chemically scrub the carbon dioxide from the thick Venusian air, molecule by molecule, across an entire planet. One proposed method is a chemical reaction known as the Bosch process. In simple terms, it works by combining carbon dioxide with hydrogen gas. The reaction produces two things we desperately need: solid graphite, which is a form of carbon, and water vapor. Think of it as a cosmic level filter, taking the primary greenhouse gas and breaking it down into a harmless solid we could store, and the very essence of life. The challenge is astronomical in scale. Where do we get the unimaginable volumes of hydrogen required? One speculative source is off-world, perhaps by diverting water-rich comets from the outer solar system or mining the ice of distant moons, a supply chain spanning billions of kilometers. Another approach looks to the planet itself, using magnesium silicate minerals. The idea is to bombard the surface with finely ground rock, creating a global reactive layer. The carbon dioxide in the atmosphere would slowly combine with these silicates to form stable carbonate rocks, essentially turning the sky into stone over millennia. This mimics Earth's own slow geological thermostat, but cranked to an impossible speed. The logistical hurdles for any of these methods redefine the word daunting. How do you distribute reactants evenly across a world with no oceans or continents to use as reference? How do you build and maintain millions of these processors in an environment that destroys conventional machinery? They would need to be self-replicating or self-repairing, guided by a distributed artificial intelligence that manages the global conversion effort over centuries. These would not be machines as we build them today. They would be more akin to slow, intelligent weather patterns made of metal and chemistry, the largest constructs ever conceived by life. They would function as the planetary lungs of a new Venus, inhaling the poisonous, thick air of the old world and exhaling the beginnings of something breathable. Yet, even if we could build such miraculous machines, a deeper question emerges, one of time and consequence. What happens to a world and to those who change it during the millennia such a transformation would require? But even the most advanced atmospheric processors would struggle against a relentless, incoming tide of solar energy. This brings us to the third and perhaps most visually stunning technological pillar, the construction of a celestial sunshade for an entire world. Cooling Venus is not just a helpful step, it is an absolute prerequisite for any meaningful surface transformation. To turn down the planetary thermostat, we must literally dim the sun over Venus, a feat of solar radiation management on a scale that defies imagination. One of the most discussed concepts involves placing a colossal solar shield at a special point in space known as the Lagrange Point 1, or L1, located directly between Venus and the Sun. At this precise gravitational balance point, an object can remain in a stable position relative to both bodies, casting a permanent, cooling shadow onto the planet. The engineering of such a structure pushes the limits of what we consider possible. It could not be a solid disk of metal that would be far too massive to construct or launch. Instead, it would likely be a cloud of billions of individual spacecraft, each one a delicate, ultra-thin film of reflective material no thicker than a soap bubble. These would be self-stabilizing using the gentle pressure of sunlight itself, a technology called a solar sail, to maintain their precise formation. Think of it as a gossamer veil woven across space, a technological lace that filters a precise percentage of the sun's fury before it ever reaches the planet's atmosphere. An alternative or complementary approach involves not one giant shield, but vast fleets of smaller reflective mirrors placed in orbit around Venus itself. These would work by increasing the planet's albedo, its reflectivity, bouncing sunlight that has already reached the cloud tops back into space before it can be absorbed as heat. Coordinating these swarms would be a ballet of unprecedented complexity, managed by a distributed artificial intelligence ensuring every mirror is angled perfectly to achieve the desired global cooling effect without creating dangerous temperature imbalances. The goal of these celestial architectures is clear: to initiate a controlled global cooling trend. By reducing the solar input, we would slow the runaway greenhouse engine, making the subsequent work of atmospheric processors infinitely more efficient. It would also protect the fledgling floating cities from the rising thermal currents below, stabilizing their environment. This is planetary climate engineering of the most direct kind, a demonstration of moving from merely adapting to an environment to actively, thoughtfully managing the energy balance of a world. Yet, as we contemplate weaving sunshades in space, we must also look down at the ground we aim to one day walk upon. What would it take to not just cool the surface, but to prepare it for a future it has not known for billions of years? Nature itself might hold the most elegant tools for this planetary scale renovation. beyond vast machines and orbital mirrors, a quieter, more organic revolution is brewing in the field of synthetic biology, where scientists are learning to reprogram the very code of life. The vision is to create custom microorganisms engineered not for a petri dish but for the alien skies of Venus. Picture a microscopic workforce, trillions strong, designed to thrive in the temperate cloud layer. These would not be simple bacteria from Earth, but entirely new forms of life built from the ground up, their singular purpose to consume the planet's most abundant and problematic resources. One strain could be crafted to metabolize carbon dioxide, using a supercharged version of photosynthesis to split the molecule, locking away the carbon and releasing pure oxygen as a byproduct. Another, more radical design might be engineered to feed on the sulfuric acid droplets that make up the clouds, breaking them down into water and sulfur, effectively detoxifying the very environment that defines Venus. This approach turns the problem into the solution, using the planet's own toxic atmosphere as the feedstock for a slow, biological conversion. We could envision deploying these microbes as a living, self-replicating haze, a photosynthetic mist that floats perpetually in the temperate zone, working silently across centuries to scrub the air. It is a profound fusion of technology and biology, where life itself becomes the most sophisticated terraforming tool we could ever deploy. Yet, this breathtaking possibility opens a deep well of ethical questions. Venus has no biosphere, no native life as we understand it, which means we would not be displacing an existing ecosystem, but we would be introducing one, and once released, these engineered organisms would be nearly impossible to recall. What if they mutate in unexpected ways? What if their metabolic processes create unforeseen and harmful secondary compounds? The challenge of containment in a global atmosphere is absolute. This forces us to consider not just the engineering, but the philosophy of planetary stewardship. Are we gardeners carefully introducing a chosen species to heal a barren world? Or are we architects imposing a complete biological blueprint of our own design? The decision to seed another planet with synthetic life carries a weight far beyond engineering, touching on our responsibility as a species that may soon hold the power to awaken entire worlds. And if we can redesign microbes for another planet, what does that mean for the future of life right here at home? The sheer scale of energy required for this project is a number that defies easy comprehension. To remodel an entire world, you must command forces on a planetary scale, and the power needed is not merely large, it is astronomical. To put it in perspective, the total energy consumed by all of human civilization in an entire year is a single drop in the ocean of what would be required to cool Venus, process its atmosphere, and sustain its floating cities. We are talking about energy budgets that span millennia, demanding a fundamental rethinking of how we generate and distribute power. The first and most obvious source is the sun itself, which bathes Venus in even more intense light than Earth receives. One visionary concept involves constructing vast solar arrays in orbit around the planet, where sunlight is uninterrupted by clouds or night. These would not be simple panels, but sprawling constellations of mirrors and photovoltaic cells, each 1 kilometer across. They would then convert that captured solar energy into microwaves or laser beams, transmitting it wirelessly down through the atmosphere to receivers on the floating cities and surface processors. It is a continuous, invisible rain of pure energy, powering the machines that rebuild the world. But solar power, while abundant, has limitations, especially when the long-term goal involves cooling the planet and potentially shading it. This is where the dream of nuclear fusion becomes critical. If the technology can ever be mastered and miniaturized, a compact, high-output fusion reactor would be the ideal power plant for a floating city or a major atmospheric processor. It would provide a dense, reliable, and constant energy source independent of the planet's weather or orbital cycles, a miniature sun contained within a magnetic bottle. There is also the potential to harness the planet's own ferocious energy. The super-rotating winds in the upper atmosphere, which whip around the planet every 4 Earth days, could spin vast airborne turbine arrays. The incredible temperature differential between the scorching surface and the cooler cloud decks could even be tapped into, using principles of thermal convection to generate additional power. Yet generating this titanic amount of energy is only half the battle. Distributing it presents a labyrinth of engineering challenges. How do you wirelessly beam gigawatts of power across hundreds of kilometers of turbulent, acidic atmosphere with pinpoint accuracy and minimal loss? How do you create a resilient energy grid that connects millions of autonomous processors scattered across a globe, ensuring that if one fails, the entire system does not collapse? This would not be a simple power grid. It would be a dynamic, intelligent nervous system for a planet under anesthesia, carefully managing the flow of energy that fuels its own metamorphosis. The energy question ultimately frames the entire endeavor in stark terms. It is a project that would consume the focused economic and industrial output of a united humanity for generations. It forces us to ask not just if we can find the power, but if we can sustain the will. The economics of terraforming Venus presents a challenge as profound as the engineering. Who pays for a planet? The scale of investment required to even begin such a transformation would dwarf the combined wealth of every nation in human history, a financial undertaking spanning not just decades but centuries. This forces us to consider entirely new frameworks for value and cooperation. One plausible model is the formation of a Venus alliance, a permanent consortium of nations pooling resources, knowledge, and political will across generations, treating the project as a shared legacy for humanity akin to a cathedral that takes 500 years to build. Its currency would be patience and sustained commitment. Alternatively, the drive could come from private entities, corporations, or visionary individuals motivated by the ultimate long-term asset, an entire world. The promise of exclusive access to future resources, from mineral rights to entirely new real estate, or simply the immortal prestige of founding a second branch of civilization, could attract staggering private capital. Yet the most compelling motive may transcend economics altogether, a global imperative for species survival. In this view, Venus becomes more than a project. It is an insurance policy for humanity, a second egg in a separate cosmic basket, justifying the investment as a fundamental act of preservation. Funding the dream is one thing, but delivering the physical means to achieve it is another universe of difficulty. The logistics are paralyzing to consider with today's mindset. Transporting millions of tons of machinery and material from Earth's gravity well to Venus would be prohibitively expensive and slow. The solution likely lies in looking outward, not just downward. The initial supply chain would bypass Earth almost entirely, instead harvesting raw materials from nearby asteroids, the moons of Mars, or other celestial bodies with weaker gravity. Robotic scouts and miners would be the first pioneers, extracting metals, silicates, and water ice to be processed at orbital shipyards around Venus. This in-situ resource utilization turns the solar system itself into our warehouse and factory. The initial infrastructure on Venus would not be built by human hands. It would be constructed by fully automated, self-replicating robotic systems. Imagine the first landers not as scientific probes, but as seeds. They would touch down in the most accessible areas and use locally sourced materials to build copies of themselves, and then those copies would build the first atmospheric processors or solar array components. This slow, exponential growth of robotic workforce would prepare the stage for centuries before the first human architects ever set foot in a floating city. The entire economic and logistical framework, therefore, demands a fundamental rethinking of time, value, and international partnership. It asks whether humanity can align around a goal whose payoff lies far beyond the lifespans of those who commit to it, viewing the transformation of a world not as an expense, but as the ultimate inheritance we could leave for the distant future. But this grand vision rests on a question far deeper than engineering or economics. It forces us to confront the philosophy of our own ambition. Is it right to reshape another world in our image? Venus may be a lifeless hellscape, but does that emptiness grant us a blank check to impose our own blueprint? Some argue that a planet, even a barren one, holds an intrinsic value in its natural state, a unique chapter in the solar system's story that we would be rewriting for our own convenience. This perspective asks us to consider ourselves not as conquerors but as guests with a responsibility to tread lightly. The ethical waters become even murkier when we consider the possibility of life. Our current understanding says Venus is sterile, but what if our probes, digging deeper or looking closer, find microbial extremophiles clinging to existence in the upper clouds or deep within volcanic vents? The act of terraforming would then become an act of planetary-scale biocide, erasing the only other known life in the universe to make room for our own. This risk alone could halt the entire endeavor, pivoting our mission from transformation to pure preservation and study. These dilemmas frame two opposing philosophies for our future role. The first is the gardener. This approach seeks not to bulldoze and rebuild, but to gently nudge, to introduce carefully chosen elements that might, over eons, guide Venus toward a more Earth-like equilibrium on its own terms. It is a posture of patience and collaboration with planetary processes. The second is the engineer. This paradigm sees a planet as a complex system to be understood, taken apart, and reassembled according to a superior design. It is an act of ultimate control, born from the belief that we can and should build a better world than nature, left alone, provided here. Our choice between these paths says everything about how we view our place in the cosmos. Are we humble stewards or audacious architects? The society that grows within the floating cities will be shaped by this foundational philosophy. Will it be a utopian outpost, a community of scientists and engineers united by a transcendent purpose, living in egalitarian harmony as they shepherd a world through its rebirth? Or will it inevitably reflect the fractures of Earth, becoming a stratified colony where the planners and technicians live in comfort in the upper cloud decks, while a labor class maintains the dangerous machinery lower down or faces the relentless hardship of early surface operations? The very structure of these cities, whether open and interconnected or divided and secured, will embody the social values of their founders. The act of terraforming is, therefore, a mirror. It is not merely a test of our technology, but the ultimate test of our wisdom, our ethics, and our ability to build a society worthy of the incredible power it seeks to wield. As we look up at that bright evening star, we are not just looking at a future project site. We are looking at a question. What kind of species do we want to become when we step off our cradle and into the wider universe? The stark differences between Venus and Mars reveal the two fundamental paths for making a world habitable. While Mars captures our imagination as a dusty, familiar neighbor, its terraforming challenge is one of profound addition. The red planet is cold and thin, its atmosphere a wispy remnant offering little pressure and no protection from radiation. To walk on its surface without a suit, we would need to thicken that air dramatically, adding vast quantities of greenhouse gases to trap heat and raise the temperature, a process of planetary-scale infusion. Venus presents the exact opposite problem. It is a world of catastrophic surplus where the challenge is one of relentless subtraction. Its atmosphere is far too thick, far too hot, and choked with the very gas we would need to add to Mars. So while Martian architects dream of factories that manufacture atmosphere, Venusian planners must design machines that dismantle it. This creates a fascinating technological symmetry. The advanced atmospheric processes we imagine for Venus, capable of filtering and breaking down carbon dioxide, could one day be reverse engineered for Mars. On the red planet, a similar machine might be tuned not to remove carbon dioxide, but to produce it from raw materials, pumping it into the thin air to jumpstart a greenhouse effect. The synthetic biology developed to create cloud-scrubbing microbes for Venus could inspire strains engineered for Mars, designed to survive in its soil, release oxygen, and fix nitrogen, slowly preparing the ground for plants. Each world becomes a laboratory for techniques that could, in modified form, serve the other. Yet there is one profound, immediate advantage Venus holds. Mars requires a complete atmospheric overhaul before its surface becomes remotely accessible. Even the most optimistic timelines span many centuries. Venus, however, offers a habitable zone right now, today, floating in its upper atmosphere. We do not need to wait for a 1,000-year climate transformation to establish a permanent human presence there. The floating city is not a distant goal contingent on planetary change. It is a feasible first step that could be built with technology on the horizon. This comparison does not crown one planet as the superior target, but rather enriches our entire approach to spacefaring. It teaches us that there is no one-size-fits-all solution for living beyond Earth. Our future may not be a choice between a red planet and a cloudy one, but a diversified civilization that learns to thrive in multiple environments, using the harsh lessons from each to inform our stewardship of all. The journey to make other worlds livable begins with understanding that every planet tells a different story, and our role is to learn its language before we try to rewrite its ending. This timeline stretches beyond nations and generations into the deep time of geology itself. To reshape Venus is not to complete a construction project, but to initiate a new chapter in a planet's biography, one that will be written over thousands of years. The first phase, unfolding over roughly the next century, belongs entirely to our robotic emissaries. Autonomous probes and drones will map the temperate cloud layer in exquisite detail, testing material samples against the corrosive environment and constructing the very first prototype habitats, small, uncrewed bubbles that must prove they can endure for decades. This is the era of relentless data gathering and foundational engineering, where every sensor reading and every material stress test builds the blueprint for what comes next. Sometime in the 2nd or 3rd century, Phase 2 begins with a profound milestone, the first permanent human settlement floating in the Venusian sky. This initial city would be small, perhaps a scientific outpost of a few hundred pioneers, utterly dependent on resupply from Earth or orbital stations. Its primary mission shifts from survival to expansion and the initiation of planetary change. From this secure foothold, the first major geoengineering projects are launched. Vast, delicate solar sails are deployed at the Lagrange point, beginning the slow, patient work of cooling the planet by filtering a fraction of the sun's intensity. In this era, humanity transitions from a visitor in the clouds to a permanent resident with a long-term plan. The true transformation commences in Phase 3, a period that likely spans the entire first millennium. With the planet now on a controlled cooling trend, the work of atmospheric processing begins in earnest. The first generation of colossal carbon scrubbers, perhaps using the Bosch process or biological agents, are activated. Their initial impact will be imperceptible on a human timescale, like watching a mountain erode. Yet, over centuries, their cumulative effect becomes measurable. The crushing surface pressure begins a slow, steady decline. Temperatures fall from the unbearable toward the merely extreme. This millennium is defined by the hum of global machinery, a silent, planet-wide effort managed by artificial intelligence and monitored by generations of cloud-born citizens who have never known Earth. Everything that follows belongs to Phase 4, a long tail of normalization that stretches across multiple millennia. The heavy lifting of atmospheric stripping is complete, but the fine-tuning remains. The new, thinner atmosphere must achieve a stable chemical balance. Temperatures must settle into a range that allows for liquid water to pool on the surface once more, something not seen on Venus for billions of years. Only then, in this distant future, could the final, most delicate step be contemplated, the seeding of a surface ecosystem. This would not be the introduction of Earth's full biosphere, but a careful, staged release of engineered lichens, microbes, and simple plants designed to stabilize the new soil and begin producing a breathable mix of gases. This perspective fundamentally reframes the endeavor. Terraforming Venus is not a task with a ribbon-cutting ceremony. It is the establishment of a permanent, evolving relationship with a world, a covenant between humanity and a planet we chose to awaken, a responsibility that becomes the central project of our civilization for ages to come. The first chapter of this new Venusian story will be written not by human hands but by silent, resilient machines. Before a single habitat drifts into the temperate zone, an army of robotic pioneers must endure the alien sky alone, gathering the data that will make everything else possible. These are not the landers of old, designed for a brief, heroic struggle against the surface. These are long-duration aerobots engineered to live within the clouds for years. Picture a fleet of intelligent blimps or solar-powered gliders, their gossamer wings and envelopes crafted from those advanced acid-resistant composites. Their mission is one of profound patience, to map the intricate wind patterns of the super-rotating atmosphere with exquisite precision, to measure the exact chemical composition of the sulfuric acid droplets, and to hang sensor arrays directly in the airstream to monitor how prototype materials degrade over months and years of exposure. Every gust of wind, every subtle temperature fluctuation, every microscopic pit on a test panel is a vital data point, building a dynamic weather model of this alien environment. This information is the bedrock upon which all future cities will be designed, telling engineers exactly how much stress a floating structure will face and from which direction the storms will come. The most critical task for these cloud scouts is to identify and prepare the first construction site. After years of atmospheric surveying, a prime location in the habitable zone would be selected, a region with stable winds and minimal turbulence. Here, the next generation of robots would arrive, autonomous drones equipped not just with sensors, but with manipulator arms and assembly protocols. Their objective is to build the very first human-made object intended to stay forever in the Venusian sky, a lightweight, unmanned platform. This initial structure might be a simple hexagonal frame, a skeletal proof of concept assembled piece by piece from materials either brought from orbit or, more likely, manufactured in situ from processed atmospheric gases. This platform serves as the foundational stepping stone, a stable dock upon which more complex modules can later be attached. It is the first stitch in a tapestry that will one day become a metropolis. The engineering challenge for these robotic builders is absolute. They must execute flawless construction in a corrosive, windy environment with no possibility of human intervention, relying entirely on pre-programmed intelligence and resilient systems. Their success would be a quiet, monumental triumph, proving that sustained, complex activity in the clouds of Venus is not just a dream, but an achievable reality. This robotic phase, spanning decades, transforms the planet from a distant object of study into a work site, setting the stage for the moment when our species finally steps into that orange haze to begin the real work of building a home. The first successful docking of a crewed capsule with that skeletal platform would mark a moment for the history books, not of a single nation, but of our entire species. Phase 2 begins with a breath held across millions of kilometers, as the first airlock hisses open and human eyes adjust to the soft, internal light of humanity's first permanent home beyond Earth. This initial habitat is not a sprawling city. but a cluster of interconnected modules, a fragile bubble of earthly biology and technology floating serenely at the 55-kilometer mark. Its design is modular and pragmatic, built to expand like a set of cosmic building blocks. Each cylindrical section has a dedicated purpose: living quarters, a communal galley, laboratories, and a command center with panoramic viewports that look out upon an endless sea of orange and yellow clouds moving in slow, silent currents. The station itself is buoyed by the very air its inhabitants breathe, a massive envelope of nitrogen and oxygen that makes the entire complex lighter than the dense carbon dioxide atmosphere outside. This is not a temporary camp, it is a declaration of permanent residence. The most critical systems are those the crew will never see, the silent, humming machinery that performs the miracle of making a sealed metal can in a poisoned sky feel like a living world. Life support is a closed-loop ballet of chemistry and biology. Every exhaled breath is captured, its carbon dioxide scrubbed by molecular sieves and fed either to onboard algae tanks or chemical processes that crack the molecule, reclaiming oxygen. Water is never wasted. Every drop of condensation, every bit of moisture from showers and humidity is purified and recirculated. Even human waste becomes a resource, processed into sterile nutrients for the aeroponic gardens. In these brightly lit modules, rows of plants grow not in soil, but in a mist of water and recycled minerals, their roots dangling in air. These gardens provide fresh food, yes, but their true value is psychological, a living, green sanctuary that smells of basil and damp earth, a stark and vital contrast to the sterile, processed air of the corridors. This self-contained biosphere is a tiny, working model of the planetary-scale conversion happening outside, a proof that cycles of life can be sustained in the void. Living within this sealed world imposes a unique psychological landscape. The outside view is perpetually the same, a beautiful but monotonous panorama of haze and cloud, with no horizon, no sunrise or sunset as we know them, just a gradual brightening and dimming of the diffused light. There are no weather changes, no passing birds, no rustle of leaves, only the constant, low hum of circulation fans and filters. This sensory sameness can be profoundly isolating, demanding new forms of mental resilience. The community becomes everything, a self-contained society of perhaps a few dozen individuals whose cooperation is not just pleasant, but essential for survival. Social structures are forged under this pressure, evolving new norms for conflict resolution, privacy, and shared purpose. Celebrations are invented for milestones like a successful harvest or the anniversary of the station's founding, creating a new calendar and new traditions under an alien sky. The crew are more than scientists. They are pioneers testing the very idea of a human society divorced from the rhythms of a natural planet. This first outpost, for all its fragility, is the seed from which an entire civilization could grow. Its primary mission is science, monitoring the robotic scouts and the first tentative geoengineering experiments, but its legacy is far greater. It becomes a living testbed for every technology and social model that will define our future in space. How do you govern a community where every resource is tracked? How do you maintain morale when the mission stretches for years and the home you left behind feels like a distant dream? The answers forged here in these modules floating in the orange glow will set the precedent for every habitat on Mars, every station in the asteroid belt, and for the great cloud cities that may one day follow. The crew, by simply living and working and growing fresh lettuce in the clouds, are doing the most radical work of all. They are learning what it truly means for humanity to call another world home. The quiet science station now becomes the command center for a planetary revolution. With a secure human foothold in the clouds, the grand and patient work of planetary change can finally begin in earnest. This is Phase 3, the industrialization of the atmosphere, where the dream of terraforming moves from the drawing board into the sky itself, transforming a research outpost into the heart of a global operation. The first visible sign of this new era is the deployment of the prototype atmospheric processors. These are not yet the continent-sized machines of the distant future, but smaller, modular units, perhaps each the size of a city block, tethered near the floating habitat. Their purpose is twofold: to prove the core technology and to provide immediate, tangible benefits to the fledgling colony. One design might work like a giant mechanical lung, using concentrated solar energy to split the thick carbon dioxide outside. The process yields two precious resources: breathable oxygen, which is pumped directly into the habitat's life support reserves, and solid carbon, which is harvested as a raw material. Imagine engineers using this harvested carbon, the very stuff of Venus's poisonous sky, to 3D print new structural beams, tools, or even components for the next generation of processors. It is a powerful symbolic turn, using the planet's greatest problem as the physical foundation for its solution. This creates the first inklings of a true off-world economy, where the byproducts of terraforming directly fuel its own expansion. Scaling up this operation requires a leap in logistics. The floating city cannot manufacture everything it needs from thin air alone. This phase demands the establishment of serious orbital infrastructure around Venus. Space stations at Lagrange points become bustling ports and shipyards, receiving automated freighters from the asteroid belt that carry prefabricated industrial modules, advanced robotics, and rare elements not found in the atmosphere. From these orbital docks, massive cargo shuttles, shielded against atmospheric entry, make the careful descent to deliver their payloads to the cloud cities. It is a continuous, delicate ballet of arrivals and departures, the supply line for a planet-sized project. Concurrently, the first elements of planetary climate management may be launched. While full-scale solar shades are a project for the centuries, this era could see the deployment of test arrays, clusters of reflective mirrors placed in high orbit. Their initial goal is not to cool the entire planet, but to study the dynamics of orbital engineering and to provide precise, localized shading for sensitive surface experiments, or to protect the growing industrial zones from solar flares. The entire character of the human presence shifts during this phase. The population grows, diversifying from a crew of scientist pioneers to include engineers, technicians, drone pilots, and construction specialists. The hum of machinery becomes a constant backdrop to life in the clouds. New floating platforms are constructed, dedicated solely to manufacturing, energy production, or processor maintenance. The venture is no longer just an outpost, it is an industrial operation with a singular, monumental product, a new world. Every gram of oxygen produced, every bar of pressure slowly reduced, is a line in a ledger that spans millennia. This is where the abstract vision becomes a daily, grinding, glorious reality, building the future one molecule at a time. Centuries of patient work finally yield a visible sign in the planetary data. The great cooling has begun. As the colossal atmospheric processors hum in their millions and the orbital sunshades filter a precise percentage of sunlight, the fever that gripped Venus for billions of years starts, molecule by molecule, to break. This is not a sudden winter, but a slow, deliberate retreat of the heat. A planetary temperature chart whose line begins an almost imperceptible but inexorable downward slope across generations. The change is measured in fractions of a degree per year, a pace too slow for any single human to feel, but recorded with solemn triumph by the descendants of the original cloud settlers. The thickening blanket of carbon dioxide, the engine of the runaway greenhouse, is being steadily dismantled. As it thins, it traps less infrared radiation, allowing more heat to finally escape back into space. The effect is compounded by the celestial mirrors, which reduce the total solar energy entering the system from the start. This dual approach, treating both the symptom and the cause, initiates the most profound metamorphosis a world can undergo, a shift in its very metabolic state. This planetary-scale intervention does not proceed in simple, linear fashion. It triggers a cascade of complex climatic feedback loops that demand constant, vigilant management. For example, as the upper atmosphere cools, the fierce super-rotating winds that once circled the planet every 4 Earth days might begin to slow and shift their patterns, altering the stable flight paths of the floating cities. Engineers must continuously adjust station-keeping thrusters and atmospheric processor placements in response. A more significant concern involves the sulfuric acid clouds themselves. Their formation and persistence are tightly linked to the high temperature and pressure. As the environment changes, this global cloud deck could begin to dissipate or morph in unpredictable ways. This presents a paradox, as the clouds, while corrosive, also reflect a significant amount of sunlight. If they thin too quickly as a result of the cooling, it could temporarily allow more solar energy to reach the lower atmosphere, creating a brief warming spike that could disrupt the carefully managed cooling trend. The climate scientists living in the sky become planetary doctors, monitoring 1,000 vital signs, running endless simulations, and making micro-adjustments to the sunshade alignments or processor outputs to guide the system toward the desired equilibrium. Their goal is to avoid any tipping point that could send the climate veering toward a new, unintended state of chaos. The most tangible evidence of success beyond the graphs is a sensation felt by the machinery venturing downward. The atmospheric pressure is dropping. For millennia, that pressure was a crushing, absolute barrier, but now it begins a long retreat. This gradual change unlocks a new era of construction and exploration. The lighter, floating habitats designed for the original dense air now find they can operate safely at slightly lower altitudes, but more importantly, it allows for the design of heavier, more permanent structures. Engineers begin to design and lower massive, anchored cables from the primary cloud cities, tethers reaching dozens of kilometers down into the thinning atmosphere. At the ends of these cables, they can suspend robust observation platforms, heavy industrial reactors, or shielded laboratories that benefit from colder temperatures. These are the first permanent human-made structures to exist below the main cloud deck, pioneers in the slowly gentling sky. They serve as weather stations, sensor arrays, and relay points, extending humanity's reach ever closer to the once forbidden surface. The act of lowering a platform on a 20-kilometer tether becomes a celebrated engineering milestone, a physical manifestation of the changing world. For the generations born in the cloud cities, this phase transforms their relationship with Venus. Their grandparents spoke of it as a hostile, alien environment to be survived. Their parents saw it as a global project to be managed, but they witness it as a world that responds. They track the cooling trends in school. They watch the external camera feeds as the cloud patterns slowly evolve over decades, and they hear the stories of how the old atmospheric pressure readings compare to the new, lower ones. Venus is no longer a static hellscape. It is a dynamic system under their care, showing the first faint signs of a new potential. This slow-motion transformation, visible only across lifetimes, fosters a unique cultural perspective, one of profound intergenerational patience and a deep sense of custodianship. The project's success is measured not in quarterly reports, but in the gentle decline of a global average temperature curve that their great-grandchildren will continue to steward. The sky they call home is gradually, patiently becoming a kinder sky. After centuries of patient cooling, the data from the cloud cities finally signals a new frontier. The surface of Venus, once an absolute no-go zone, has entered a new phase. It is no longer a molten forge, but a world settling into a deep, rocky simmer. This marks the beginning of Phase 5, a distant era where humanity's project shifts its gaze downward, from managing the sky to actively preparing the ground. The surface is still brutally hostile, with temperatures perhaps in the hundreds of degrees and pressures still many times that of Earth, but the environment has crossed a critical threshold. It is now a place where specially hardened machines can survive, work, and most importantly, begin to build the foundation for a world to come. The first entities to touch down in this new age are not human explorers, but robotic landers of unimaginable resilience. These are not the delicate probes of centuries past, but bulldozer-sized automatons, their shells crafted from ceramics and refractory metals that laugh at the heat. Their mission is one of planetary-scale groundwork. One of their primary tasks could be to initiate the first direct biological intervention on the surface. Picture them deploying canisters that release not chemicals but trillions of microscopic seeds. These are not ordinary spores, but genetically engineered lichens, designed in orbital laboratories over generations. Their purpose is simple and profound: to survive. They are programmed to cling to the bare volcanic rock, using the scant traces of water vapor and processed atmospheric gases to slowly, over decades, form a thin, living crust. This biological net would do two things: stabilize the dusty, loose regolith against the still powerful winds, and through their metabolism, begin the microscopic work of breaking rock into something that could one day resemble soil. It is the first faint green whisper on a world of gray and orange, a promise written in biology. Concurrently, another robotic army would tackle the most precious resource of all: water. Venus has almost none on its surface, but its atmosphere holds the elemental ingredients, hydrogen and oxygen. Enormous, stationary processing plants, anchored to the highlands, would begin the monumental task of synthesizing water directly from the air. Using vast amounts of energy beamed down from orbital solar arrays, these factories would crack carbon dioxide and sulfuric acid, combining the liberated hydrogen and oxygen atoms. The output would not be rivers, but a slow, deliberate trickle collected in massive, insulated containment ponds. These first reservoirs would sit steaming under the dim sky, the first open bodies of liquid water on Venus in billions of years. Their initial purpose is not for drinking, but for climate regulation, as water vapor becomes a key greenhouse gas to carefully manage the ongoing cooling, and as a resource for the next phase of biological expansion. To accelerate the cooling of the very ground, engineers might deploy fields of another kind of machine, heat-dissipating radiators. These would be vast, metallic fins or networked pipes covering square kilometers, designed to pull geothermal heat from the crust and radiate it more efficiently into the atmosphere, where the thinning air can finally carry it away into space. The surface in this long era is a global construction site of staggering scale and patience. It is a place of silent, automated industry, where the goals are measured in centimeters of soil formation and degrees shaved off a global average over a century. For the citizens in the cloud cities far above, the surface remains a place viewed through sensor feeds and data streams, a fiery workshop being slowly, methodically tamed. It is not yet a home, but it is no longer a hell. It is becoming a project, the solid foundation upon which the final, most delicate act of planetary creation might one day be possible. Millennia of patient work culminate in a sight that would stun the original cloud-born pioneers. Venus has awakened. The planet now spins beneath a sky of soft blue, streaked with white water vapor clouds. Vast, shallow oceans born from synthesized water and the slow condensation of the reformed atmosphere shimmer across the lowlands, reflecting the gentle sunlight that now filters through. The crushing pressure is a distant memory, replaced by an atmospheric pressure nearly identical to Earth's at sea level, a mix of nitrogen and oxygen that fills the lungs with a crisp, clean breath. The global temperature has settled into a temperate range, allowing for liquid water, weather cycles, and the possibility of rain falling on a solid surface for the first time in billions of years. This is the ultimate vision realized, a terrestrial twin, a second Earth orbiting a little closer to the Sun. Yet this new world carries the indelible signature of its creation. The geography tells a hybrid story. The great continent-sized highlands like Ishtar now rise as rugged, mountainous archipelagos from global seas. Their slopes are terraced with the foundational soils first established by engineered lichens, now supporting complex, introduced ecosystems. The lowland plains are oceanic basins, their floors a testament to the ancient volcanic fury that once ruled here. This is not a replica, but a sibling, a planet with Earth's vital signs but Venus's own bone structure and a history unlike any other. Most strikingly, the sky itself holds a living monument to the journey. Suspended in that now breathable air at their original altitude, the great floating cities remain. They are no longer life rafts in a poisoned sky, but preserved wonders. Some have been transformed into vast museums and universities, their original modules maintained as historical sites where visitors can walk the same corridors as the first cloud settlers. Others have become unique resorts or agricultural centers, tending to specialized crops in their controlled biospheres, drifting serenely between the weather patterns they helped to create. Their existence creates a layered civilization, with communities on the new surface looking up to see the glittering jewels of their own ancestral homes sailing through a friendly sky. This duality is the project's deepest lesson. We did not simply overwrite one world with another. We guided a transformation that honors both the original planet and the new potential. The result is a testament to a stewardship that thinks in geological time, that values patience over conquest, and that understands a home is not just a place you find, but a story you build generation by generation across the ages. The grandeur of this vision is matched only by its profound vulnerability. Any project that seeks to reshape a world over millennia must confront the sobering reality of catastrophic failure, where a single miscalculation could unravel centuries of patient work. The most immediate and terrifying risk is the structural collapse of a major floating city. Picture a critical failure in the envelope's self-healing polymer, perhaps from an unpredicted chemical interaction with a new atmospheric compound or an impact from dense debris. The breach would not be a slow leak but a violent decompression. The breathable air inside, which provides the city's buoyancy, would erupt into the thinner carbon dioxide atmosphere outside. The entire structure would lose lift catastrophically, beginning a fatal descent into the deeper, hotter layers of the atmosphere. Within minutes, the city would plunge from its temperate haven into a thickening, scorching hell, its materials melting long before it ever reached the surface. The human cost would be unthinkable, a tragedy on a scale never before seen off Earth. This scenario forces engineers to design not for single points of failure, but for distributed resilience. Each major habitat would need to be a cluster of independent, sealed modules, so that a breach in one section could be isolated, its atmosphere sacrificed to save the rest. Redundant lift systems, perhaps separate internal gas cells, would act as lifeboats providing emergency buoyancy. The entire city's architecture would be a lesson in graceful failure, ensuring that even in disaster, some remnant could survive. Beyond the cities, the planetary-scale machines themselves harbor their own apocalyptic potential. An atmospheric processor network spanning the globe and operating for centuries is a monument to complex chemistry. What if a cascade of errors, perhaps a software bug or a corrupted feedstock supply, triggers a runaway reaction? Instead of cleanly converting carbon dioxide into graphite and oxygen, the process could veer off into producing vast clouds of carbon monoxide or other toxic compounds, poisoning the very air the floating cities breathe and setting the atmospheric conversion back by generations. Similarly, the celestial sunshade is a delicate equilibrium. A major collision in the Lagrange point, or a systemic flaw in the solar sail alignment software could cause a section to collapse or misalign. The result would be a sudden, focused beam of unfiltered sunlight lancing onto a region of the planet, triggering violent thermal storms and undoing decades of careful cooling in a matter of days. These are not mere engineering puzzles, they are existential threats to the entire endeavor. The solution lies in building stupendous redundancy and diversity into every system. Multiple, independent processor designs would work in concert, so if one fails dangerously, others can be shut down or adjusted to compensate. The solar shade would be composed of countless independent units, so that the failure of thousands would only dim its effect slightly, not collapse it entirely. The guiding principle must be that no single error, however large, can be terminal. The risks are not only technological but deeply human. A project of this duration and cost would inevitably become a geopolitical entity, a new world with unimaginable resources. The potential for conflict is a shadow that follows ambition. Disputes could arise over the allocation of processed materials, the control of energy beamed from orbit, or the governance of the newly stable surface. If the cloud cities or surface territories fracture into rival factions, the tools of planetary transformation could become weapons, threatening to deliberately destabilize the climate or destroy vital infrastructure. More subtly, the will to continue might simply fade across generations. The descendants living in comfortable, fully realized cloud cities centuries from now may see the ongoing, grinding work of surface transformation as a distant, expensive abstraction, a project for their ancestors with no tangible benefit to their own lives. Political movements could arise to abandon the surface work entirely, to preserve Venus as a cloud-born civilization and cease the risky planetary engineering. This intergenerational drift is perhaps the most insidious risk of all, a slow abandonment of the original covenant not through disaster, but through changing priorities and forgotten purpose. Guarding against this requires building a culture that venerates the long-term goal, that educates each new generation in the why as much as the how, and that structures governance to protect the project's continuity across centuries, even when immediate utility is hard to see. Confronting these dark possibilities is not an exercise in pessimism, but the bedrock of responsible creation. It means designing every system with multiple overlapping safety protocols, managed by decentralized artificial intelligences that can contain local failures. It means establishing clear, resilient treaties and governance structures from the very beginning, frameworks designed to endure political shifts on Earth and in the clouds. Most importantly, it means cultivating a mindset of humility alongside our ambition. We are not masters imposing our will upon an inert rock. We are stewards intervening in a dynamic, complex system of almost incomprehensible power. Every action has a reaction, every solution breeds new challenges. By staring unflinchingly at the ways this dream could shatter, we are not admitting defeat, we are making a solemn promise to the future. We are committing to build a second home not as a fragile monument, but as a resilient, living world capable of enduring long after its architects are gone. The true test of our readiness to terraform Venus may not be whether we can start the process, but whether we have the wisdom to foresee how it could end and the courage to build safeguards against that ending. The quest to reshape another world may first reshape our own. Every technology forged in the corrosive clouds of Venus, every material engineered to withstand its fury, carries a profound secondary promise, a cascade of innovation that could flow directly back to Earth, solving problems we face today. This is not a distant side effect, but a core motivation, making the investment in such a grand vision pay dividends long before the first floating city is even built. The most immediate gift would be in the fight against our own planetary crisis. The atmospheric processes designed to strip carbon dioxide from the Venusian sky on a planetary scale represent a monumental leap in capture technology. Imagine scaling down these systems to human size. We could deploy them not as global solutions overnight, but as ultra-efficient filters for power plants, industrial centers, and even within the ventilation of large cities. They would not merely capture carbon, but convert it on-site into stable, solid forms of carbon that could be used in manufacturing, creating a circular economy where pollution becomes a resource. This is not science fiction. It is a direct translation of survival technology for one world into healing technology for another. The relentless acid rain of Venus demands materials we can barely conceive of today, substances that laugh at corrosion. Developing these superalloys and self-healing polymers would revolutionize industries on Earth where chemical resistance is a matter of safety and longevity. Think of chemical plants and refineries where leaks and structural degradation pose constant risks. New piping and storage tanks made from Venus-inspired composites could last for centuries without failure, dramatically improving industrial safety and reducing environmental hazards. The same advanced ceramics designed for external habitats could lead to new, incredibly durable coatings for bridges, ships, and offshore platforms, fighting the constant battle against rust and decay in our own salty, wet atmosphere. The pursuit of a home in a toxic sky would make our terrestrial infrastructure more resilient and far longer lasting. Even the architecture of the floating cities themselves inspires new possibilities for Earth. The principles of ultra-lightweight, pressurized structures that derive stability from their environment could transform how we build in challenging locations. Imagine disaster relief shelters that can be air-dropped and self-inflate into stable habitats, or research stations for the Arctic or deep deserts that are both incredibly strong and easy to transport. The closed-loop life support systems perfected for a city in the clouds are the ultimate model of sustainability. They recycle every drop of water, repurpose every bit of waste, and produce food efficiently in compact spaces. This exact technology blueprint could be applied to create truly sustainable ecologies on Earth, dense urban centers that have a near-zero ecological footprint, minimizing water use and eliminating waste. The Cloud City is not just a vision for Venus, it is a prototype for the future of sustainable living anywhere. Perhaps the most poetic return would be in how we move through our own skies. The aerostats and dirigibles designed for Venusian exploration, powered by efficient engines and capable of long-term, stable flight, could inspire a renaissance of lighter-than-air travel on Earth. These would not be the blimps of the past, but intelligent, solar-powered vessels for cargo transport, ecotourism, or as stable platforms for telecommunications and atmospheric research, offering a low-energy alternative to planes and helicopters for certain tasks. The challenge of Venus, therefore, acts as a powerful catalyst. It forces our science and engineering to leapfrog generations, tackling problems with an urgency and creativity that routine, incremental progress rarely demands. In striving to create a breath of Earth in the clouds of another planet, we may well develop the tools to ensure our own atmosphere remains breathable for millennia to come. The greatest legacy of terraforming Venus might not be a second Earth in the sky, but a renewed and sustainable first Earth right here at home. Such a monumental undertaking could never belong to a single nation or company. The transformation of Venus would require a new model of human cooperation, one that transcends borders and merges public vision with private capability. This is where the political and economic architecture of the project becomes as critical as the engineering. The first major stakeholders are the world's great space agencies, each bringing irreplaceable expertise. NASA's deep experience with planetary science and complex systems integration would be foundational. the European Space Agency could contribute advanced robotics and closed-loop life support research. Roscosmos holds decades of knowledge about surviving harsh environments from its Venera legacy. China's National Space Administration, with its rapidly advancing launch capacity and lunar ambitions, could provide crucial heavy lift and construction capabilities. Their collaboration would form the scientific and exploratory backbone. Yet these agencies alone lack the sheer industrial muscle and risk-tolerant culture needed for the construction phase. This is where private aerospace entities enter the picture. Companies like SpaceX, with their vision of interplanetary transport and reusable rockets, could establish the high-frequency, low-cost cargo routes from Earth orbit to Venusian space that make the supply chain feasible. Blue Origin's focus on in-situ resource utilization and large-scale space infrastructure could be directed toward building the orbital shipyards and processing stations around Venus itself. Their role would be to build the highways and ports that make the grand project logistically possible, but even this public-private partnership may not be enough. The most likely outcome is the creation of an entirely new entity, perhaps a Venus Development Corporation. This would be an international treaty organization with a charter spanning centuries, endowed with the legal authority to manage the terraforming process, allocate resources, and govern the initial settlements. It would function like a cross between a space agency and a sovereign development bank, issuing bonds, managing intellectual property, and ensuring that the technological fruits of the venture are shared under fair principles. The political engineering required is daunting. Existing space law, like the Outer Space Treaty, provides a basic framework declaring that celestial bodies are the province of all humankind, but it is silent on the specifics of planetary-scale alteration or the governance of permanent off-world settlements. A new suite of agreements, a Venus Convention, would need to be negotiated. It would have to address profoundly novel questions. How are mining rights on asteroids for Venusian construction allocated? Who owns the atmospheric carbon once it is processed into solid graphite? How are disputes between Cloud City residents and the governing corporation resolved? The treaty must be designed to prevent the destructive rivalries of Earth's history from being exported to a new world. It must enshrine the principle that the terraforming of Venus is a common heritage project, with its benefits, from scientific data to spin-off technologies, flowing to all participating nations and ultimately to all of humanity. The goal is to avoid a scramble for celestial real estate and instead foster a shared generational mission. This framework would need built-in incentives for cooperation and severe penalties for actions that jeopardize the global effort, such as unilateral geoengineering or the weaponization of orbital infrastructure. Success would mean that the most complex project ever attempted becomes a unifying endeavor, a proof that our species can coordinate not just across continents, but across centuries for a purpose greater than any one generation. Long before the first processor hums to life, the dream of Venus will have already taken root in our collective mind. This vision of cloud cities and a reborn world is not waiting for engineers to draw the first blueprint. It is already flourishing in the realm of art and story, shaping how we see our future. For decades, science fiction has been the primary architect of this possibility. Authors like Kim Stanley Robinson, in his novel Blue Mars, wove intricate narratives where the terraforming of Venus is not just a backdrop, but a central, driving human drama. These stories do more than predict technology. They explore the social upheavals, the ethical dilemmas, and the profound personal transformations of living through a planetary rebirth. Visual artists and concept designers translate these ideas into breathtaking imagery, rendering floating metropolises adrift in golden haze or depicting the first rain falling on a newly cooled plain. This artistic foresight is not mere entertainment, it is a vital form of public engineering. It makes the staggering scale of the project feel personal and imaginable, fueling public wonder, and, in turn, generating the cultural momentum that can sustain scientific interest and political will across generations. The dream sells itself long before a single dollar is appropriated. As the project transitions from fiction to fact, the culture it generates will evolve in a profound feedback loop. The first settlers in the cloud habitats will not just be engineers and biologists, they will be poets, musicians, and storytellers. Their art will be born from a sensory experience unlike any in human history, the perpetual soft light, the silent drift through an endless orange sky, the profound detachment from any solid ground. What does music sound like when composed in a city that gently sways with atmospheric currents? What stories are told when the horizon is a uniform haze and the only weather is the slow dance of sulfuric acid clouds below? Their literature will grapple with new definitions of home and belonging, of community forged in a sealed environment where every breath is a shared, recycled gift. This nascent Venusian culture will, in its infancy, still draw heavily from earthly traditions, a comforting echo of the world left behind. But with each passing generation born in the clouds, a unique aesthetic will emerge, one that reflects the reality of a sky-bound civilization. Their art might celebrate fluidity and interconnection, mirroring the modular, expanding nature of their cities. Their myths and heroes will likely be the quiet troubleshooters who averted a system's failure, or the patient botanists who cultivated the first sustainable garden in the void, rather than conquerors of land. This cultural output will then beam back to Earth, not as data but as soul. The songs, stories, and visual art created in the clouds will become the most powerful ambassador for the project itself. They will translate cold engineering milestones into human experience, making the transformation of a distant planet feel emotionally immediate to billions on Earth. A symphony composed to mirror the slow cooling of a world, or a novel about a child who has never felt rain but tends the city's water reclamation systems, can build a deeper connection than any technical report. In this way, culture ceases to be a side effect and becomes a core pillar of the endeavor. It maintains the vital thread of empathy and shared purpose between two branches of humanity separated by millions of kilometers. The art born from Venus will remind Earth why the struggle matters, nurturing the sustained will needed for a millennia-long project. Ultimately, the terraforming of Venus may be remembered not just for the world it built, but for the entirely new human perspective it forged, a culture born not from the soil, but from the sky, forever altering our sense of what it means to be at home in the universe. A natural question arises from this grand vision. Why Venus? Mars seems the obvious next step, a familiar desert world waiting just next door. This skepticism is both valid and vital, for it sharpens our understanding of what each path truly offers. Mars presents a compelling case with its familiar day length, polar ice caps, and a surface we can already land on. Its terraforming challenge, while immense, is one of addition, thickening a thin atmosphere and warming a cold world. Yet this very familiarity can obscure the profound, immediate advantage hidden in the clouds of Venus. On Mars, even after centuries of work, stepping outside will always require a pressurized suit, a permanent barrier between human skin and the alien environment. On Venus, that shirt-sleeve environment already exists, floating 50 kilometers high. The atmospheric pressure and temperature in that cloud band are the closest match to Earth's surface conditions found anywhere in the solar system. This is not a distant promise but a present reality. The difference in gravity is another fundamental divergence. Mars's gravity is only about 38% of Earth's, a condition that leads to severe long-term health issues like muscle atrophy and bone density loss, problems we do not yet fully know how to solve for permanent settlers. Venus, by beautiful contrast, has a surface gravity 90% of Earth's, A cloud city, while floating, would experience this full, healthy pull, allowing human bodies to develop and thrive normally across generations. The energy picture is equally stark. Mars receives only about 43% of the solar energy that Earth does, making power generation a constant constraint. Venus, being closer to the Sun, is bathed in nearly twice the solar flux. For a civilization running on sunlight, this is an abundance that could fuel not just survival, but expansive industry. Framing this as a simple either-or choice, however, misses the larger strategic picture. These are not rival destinations, but complementary chapters in a single human story. They represent two distinct technological pathways, each teaching us different, invaluable lessons. The struggle to build sealed bases and manufacture atmosphere on Mars develops expertise in extreme surface construction and resource extraction from regolith. The fight to create and sustain floating cities in the corrosive Venusian sky pushes the frontiers of materials science, closed-loop life support, and atmospheric processing. The technologies forged in these contrasting crucibles will cross-pollinate, each making the other more feasible. Pursuing both is the ultimate hedge for our species' future. It ensures that a catastrophic setback on one world, whether a plague in a sealed Martian colony or a structural failure in a cloud city, does not spell the end of our multi-planetary ambitions. Our eggs are in two separate, vastly different baskets. One path leads to a red desert we must patiently fill with air and warmth. The other leads to a golden sky where we can breathe freely from day one, while we undertake the slow, patient work of cooling the furnace below. The choice is not between Mars and Venus. The wisest, most resilient future lies in learning to walk and to float on both. Venus, transformed, offers more than a second home. It becomes a springboard, a launch complex for a future we can only glimpse from here. The very atmosphere we labored to tame now presents a unique strategic resource. That thick blanket of carbon dioxide, once the enemy, could be harvested as a nearly limitless source of propellant. Imagine orbital fuel depots, processing stations that crack the atmospheric gas into carbon and oxygen. The oxygen is life, but the carbon can be refined into advanced composites for construction. More critically, the process yields vast quantities of chemical fuel, stockpiled in orbit around Venus. For spacecraft embarking on missions deeper into the solar system, to Mercury or the asteroid belt, this changes everything. Instead of hauling every drop of fuel from Earth's deep gravity well, ships could depart from Earth orbit with minimal tanks, travel to Venus, refuel from these orbital depots, and then leap outward with a full load. Venus becomes the ultimate cosmic gas station, its position closer to the Sun providing a gravitational slingshot effect that makes journeys outward more energy efficient. This logistical advantage reshapes the economics of the entire inner solar system, but the vision extends beyond fuel. Consider the challenge of building truly interstellar vessels, ships with massive rotating habitats for multi-generational crews or vast light sails kilometers across. Constructing such leviathans on Earth and launching them against our planet's gravity is a nightmare of engineering. In the calm, dense upper atmosphere of a terraformed Venus, however, we could build shipyards in the sky. Enormous construction docks could float at the edge of space, where the atmospheric pressure provides stability but the gravity is still manageable. Here, using materials mined from nearby asteroids and processed in Venusian orbit, we could assemble spacecraft of a scale impossible on any terrestrial surface. These vessels would be launched not with explosive rocket fire, but gently nudged upward, climbing out of the atmosphere on efficient, low-thrust engines until they reach the void. This capability transforms Venus from a destination into a factory, the industrial heart of a growing interplanetary civilization. With its stable, Earth-like environment and its position as a transportation nexus, a terraformed Venus would naturally evolve into the central hub of the inner solar system. Its cloud cities, now linked by a network of aerial transit and orbital elevators, become centers of commerce, diplomacy, and scientific research unparalleled anywhere else. Think of it as a new Alexandria, a melting pot where Martian geologists, asteroid miners, and Jovian system researchers converge to share knowledge, trade resources, and plan the next great leap. The planet's location makes it an ideal command post for operating swarms of robotic probes to study the Sun up close or to manage the intricate mining operations in the asteroid belt. This perspective fundamentally reframes the entire centuries-long project. Terraforming Venus is not merely about creating a duplicate Earth. It is about building the most critical piece of infrastructure humanity will ever possess, a central port in the cosmic ocean. It is the bridgehead that turns our solar system from a collection of distant, forbidding points of light into a connected, accessible neighborhood. The investment of millennia pays a dividend not just in a new world to walk upon, but in granting our species the keys to the rest of our celestial backyard. From this vibrant, cloud-draped hub, the children of Earth, Venus, and Mars could look outward, their vessels fueled by the air of a reborn world, and set sail for the stars beyond. The symphony of engineering and biology required to awaken Venus would play across a score of millennia. This journey from the first floating platforms to a world with blue skies and oceans is not a promise of a quick fix, but a testament to our species' most profound capacity, the ability to think and act across generations. It asks us to see a planet not as a static rock, but as a dynamic system, a potential that we could help realize over a timescale that dwarfs our own lifespans. The sheer act of committing to such a vision would itself be a transformation, forging new frameworks for global cooperation and redefining our relationship with time, legacy, and our place in the cosmos. The challenges are, without question, staggering. They demand leaps in technology, unprecedented political unity, and a financial commitment that would span centuries. Yet, it is in the pursuit of this impossible dream that we find its most immediate value. The quest to build a home in a toxic sky would force innovations that cascade directly back to Earth, from ultra-efficient carbon capture systems and self-healing materials to perfected models of closed-loop sustainable living. The need for international collaboration could forge lasting bonds, turning a divided planet into a unified team with a shared, transcendent purpose. So the ultimate question posed by this cloud-wrapped world is not merely one of technical feasibility. We already possess the fundamental scientific principles to begin. The deeper question is one of courage and vision. Do we dare to begin a story whose final chapters will be read by our descendants 1,000 years from now? Choosing to try would be an act of profound hope, a declaration that humanity's story is not a brief, fleeting spark, but an enduring flame meant to spread. If we take that first, deliberate step, we will be doing more than sketching cities in an alien sky. We will be building a future where life from Earth has more than one home, ensuring that the light of consciousness finds a way to endure, no matter what fate awaits our pale blue dot. What do you think of this cosmic vision? Could we ever unite behind a project of such scale and patience? Share your thoughts in the comments below and subscribe to join us as we continue exploring the frontiers of what's possible.